Okay, so let's see. I want to start off just by taking a look again at what we did yesterday, trying to summarize that before we go on today. So what we said yesterday was we've got the standard model of particle physics, which is remarkably successful. Perhaps one of the simplest predictions we may want to verify is, well, the standard model predicts there's such a thing as an electron. What would we tell an experimentalist to measure if we wanted this experimentalist to measure an electron? And we said that a good thing to ask an experimentalist to measure would be the energy of the electron and momentum of the electron, because knowing these quantities, we could calculate the mass. We then said, but hang on, what momentum should the electron have? In which direction should it be going, and what should the magnitude of that momentum be? And we concluded that, in fact, it does not matter. The electron can be moving in any direction. It can have any magnitude, and the mass that we measure will always be the same. So this was a good label for the electron. And we wanted to get some insight into whether there were other good labels and why this was a good label. So the way that we said that we would tackle this problem is we would have some sort of an operator which would implement a transformation on our electron. So it could do something like change the direction of the momentum of the electron, or perhaps if the electron was at rest, give it some non-zero velocity. And our question then became, which labels for the electron would be invariant under that set of transformations? To start making progress with that question, we extracted a couple of properties that we said were true for any set of transformations. And this led us to the definition of a group. We then said, well, this is true for any set of transformations we may want to consider. So let's write down something that's more specific that would be consistent with only one group. And what we did to do that was the multiplication table. So we refined our closure axiom. We said, if we take this element and compose them, we will get that element. And that was a characterization, complete characterization of the group. We then saw that we were able to realize that multiplication table in terms of a number of different sets of objects with a number of different rules for how we compose the group elements. And another thing that is clear is that by using one of these concrete representations of the multiplication table, we may be able to derive certain equations which don't follow as a consequence of the multiplication table, but they also use some properties of the explicit realization that you are looking at. Because of that, we wanted to make a distinction between a representation of the group and the abstract group itself. We then asked ourselves, well, how many representations are there? We quickly learned that if we had even a single representation, we could find an infinite number of other representations which were equivalent to the representation that we had. If we had even a single representation, we could build up an infinite number of representations from this one by just taking some sort of a block diagonal form. So we said we had a whole lot of representations that were that could be built just by repeating our basic representation. And we called representations of that form reducible. Yesterday, we stated our intention that we were going to focus on equivalent reducible representations. One question that I was asked a couple of times yesterday, so let me give the answer to that, I didn't say this explicitly, was the following. If I have a matrix acting on a vector, which gives me, let's give this a label I, vector I. When I want to calculate the trace of this matrix, I can calculate the trace of that matrix in any basis that I want to. Okay, the result of calculating the trace is basis independent. You can check that for yourself because of cyclicity of the trace. So what we learn is the trace of matrix M is a sum from I is equal to 1 to D of lambda I. So when I was equating traces, some of you weren't sure how was I turning that into a statement between eigenvalues. Well, just go to the basis in which M is diagonal, and you'll see why tracing M was a statement about eigenvalues. Okay, so let's proceed now. So this is great. we claim that we have a way to characterize a group by giving its multiplication table. So perhaps we should stop now and ask ourselves, well, how good is this characterization? Well, it turns out that this characterization is awful. It's not useful for most of the cases that we're interested in. You see, you might be interested in something like a translation. Now, if I want to specify a translation, I have to specify the displacement through which I will translate. There are an infinite number of different displacements through which I could translate. So even if I just wanted to write down all of the group elements, I would never finish writing them all down. So forget about constructing a multiplication table. That I won't be able to do because I couldn't even list all of the elements. Same thing with rotations. I have to specify an axis about which I rotate. Well, that's got 2 angles in it. And I have to specify an angle through which I will rotate about that axis. Once again, that means that I'll have an infinite number of group elements. I can't list them all, so I can't stick them all in some table and tell you what they multiply to give. However, both rotations and translations are examples of what we call continuous groups. Now, when we have a continuous group, we can change the group elements smoothly. So we could say start from the identity and smoothly build up a bigger transformation. And that's what we're trying to do. So I've got a little demonstration of this. So what we're going to do, we're going to start off with a discrete transformation, and we're going to try to build up something that is continuous. Okay. So the case that I would actually like to start off with is a translation. So let's consider a function f of x. Under an infinitesimal translation, what will f of x do? F of x will go into the f of x plus epsilon. Well, you know what? Maybe if I perform an infinite number of these infinitesimal translations, maybe I can build up a finite translation. So maybe the only thing that I need to understand is infinitesimal translations. I'm now going to try to argue that what I've just said is correct. So how can I write the f of x plus epsilon? Well, if epsilon is small enough, I can write this as 1 plus epsilon d by dx acting on f of x. Okay. So what I would now like to do, I would like to say, well, let's try to build a finite translation. I am going to perform n translations. Each translation translates by some a divided by n, so that when I've done n of them, I will have translated through some finite displacement a, and I'm going to take n to infinity. So I'm taking n to infinity, and a is fixed, which is the displacement through which I want to move. So what do I have to study? Well, this is the thing I want to study. I've got 1 plus a divided by n d by dx raised to the power of n acting on f of x. And I want to take a look at this operator when n is very, very large. Okay? So let's try to figure out what that will be. Okay. So we've got u is equal to 1 plus a over n d by dx to the power of n. And I'm going to take the log of both sides. It's easier to study the log. Now, what do I mean when I take a look at this expression? How can I take the log of d by dx? I mean, this is an operator after all. Well, this side would be defined by power expanding the log. And then you would get d by dx acting on whatever you wanted. Well, if n is very large, this over here is going to be small. So I can write I've got n, and the log of 1 plus x when x is very small is just x. And when I write this down, I am neglecting terms of order 1 over n squared. When I multiply my n through, I just get a d by dx plus order 1 over n. Okay? That's log u. So what will u be? Well, u would just be equal to e to the a d by dx. Okay, so this would become e to the a d by dx acting on f of x. And we can now expand out that exponential. So I'm sure everybody knows the expansion of an exponential. Acting on f of x. Does anybody recognize this expression to be anything? What is this? This is the infinite order Taylor approximation to the f of x plus a. Okay, is everyone happy with that? So what we've been able to do is we really have been able to build up a finite translation by composing an infinite number of these infinitesimal ones. Now, when we write this e to the a d by dx, so this is now my translation operator, t of a is equal to e to the a d by dx, the way that I usually write it is I include some i's. I write this as e to the I a p, where p is equal to minus I d by dx. Now, why would I want to do that? Why do I include the extra i's in the definition? Well, there's a good reason for doing this. If I have an expression of e to the I alpha times by some operator O, okay, so this is some transformation that I could be considering. Okay, if I'm working in quantum mechanics, what would I like to have of that operator? Well, if I've got some sort of a transformation that would say boost an electron or rotate an electron or something like that, I would still like that the electron's wave function is normalized to 1. It's just now a boosted electron or a rotated electron, but I still have an electron. So what I would like from my transformation, I would like it if it doesn't change the normalization of my state. So it leaves my inner product invariant. Operators that leave your inner product invariant are unitary. So in quantum mechanics, the types of operators that we want to focus on are unitary operators. Let's write down the condition for this thing to be unitary. If this is unitary, what must we have? We must have the Hermitian conjugate of this thing must be equal to the inverse of this thing. Well, if we take the dagger, that changes the I into a minus I. So we get an e to the minus I alpha, and O becomes O dagger, must be equal to, on the other side of the equation, to get the inverse, I just change the sign in the exponential, O. So what I learn is, for these two to be equal, I learn that O dagger must be equal to O. That's a Hermitian operator. In general, then, the operator that you stick here that is going to give you the finite transformation will be a Hermitian operator. And in general, Hermitian operators are observable. That's why it was no big surprise here that when we were looking at translations, we got hold of the momentum operator. That will be true in general, and that's why I'm including this factor of I here in my definition of the generator. Okay, so a bit of language now. I call P the generator of the transformation, and you can see that even though there may be an infinite number of T's labeled by this parameter A, there is only one generator. So if I decide, instead of focusing attention on the group element, if I instead decide to focus attention on the generator of the transformation, now I again have a finite list. Okay? So I could now start to study this finite number of generators and try to study the properties of the generators. Okay, one more example that I wanted to look at of this, which doesn't use an operator, just a matrix, is, well, is the following. Let's consider a rotation. So we have, under rotation, the vector xy goes into x prime, y prime. And this is equal to, so you've all seen how vectors are rotated into each other. Acting on xy. And what do I want to do? Well, I would like to consider an infinitesimal rotation in exactly the same way that I considered an infinitesimal translation. So let me put theta equal to epsilon infinitesimal. What would the cos of theta be? This will be 1 plus order epsilon squared. Everyone happy with that? Okay. Just Taylor expansion. Sine theta would be equal to sine epsilon. Let me put the epsilon in here. Sine epsilon would be equal to epsilon plus order epsilon cubed. So what would this matrix turn into? This would be 1, 1 minus epsilon, epsilon, xy, which can be written as 1 plus I epsilon into naught I minus I naught xy. So you can see that I've written this in exactly the same form as the translation case. So this thing sitting over here that is now my generator of my rotations. Okay? And let's see, is this really true? Well, if it is really true, then I claim that a rotation by a finite angle, so let's say some rotation as an angle theta, would be given by e to the I theta t. So let's check and see if that's true. Okay, so I'm going to ask you to check, well, this is a trivial thing, right? You can check that t squared naught I minus I naught, naught I minus I naught. So you do that matrix multiplication, you will just get the identity. So t squares to 1. Now let's use that in this expression. If I power expand this thing, I find I'm getting a 1 plus I theta t minus theta squared over 2 factorial times by 1 minus I theta cubed over 3 factorial times by t, and so it continues. So this looks like 1 minus theta squared over 2 factorial plus multiplied by 1. And over here we have I theta minus theta cubed over 3 factorial, and so it continues, multiplied into 2. If you were to calculate the higher terms here, you'd see you're just getting a cos theta. This is what you're building up. So this is cos theta times by 1 plus I, and here you're building up a sine theta. Sine theta times by t, so that would be if you add up all of the terms. So now let's assemble these two. Well, cos theta multiplied by 1 will tell me I'll get a cos theta on the diagonal, a cos theta on the diagonal. I multiplied by t, I multiplied into that, I gives me a minus. So I would get a minus sine theta, and the I multiplied into that minus, I gives me a 1. So over here I would get a sine theta, and I have again reproduced the finite rotation. Okay? So I gave you 2 examples of this because this is actually a very general rule that is important, that you need to know, and it's the following. If you have the generators of a group and you exponentiate it, you will get a group element. That is an absolutely general statement about how the generators are related to the group elements. Something that was not typical here is that in the two examples that I considered, I had a single generator. I had a single generator for my translations. I had here a single generator for my rotations. That's not true in general. If I wanted to perform a rotation, a translation, in 3 dimensions, well, the operator that would do that would now be labeled by a vector displacement, and that would look like e to the I. We would have the x component of A multiplied by px. We would have the y component of A multiplied by py, and the z component of A multiplied by pz. Okay? But now we can see another general rule emerging. To specify a translation, over here I have to specify 3 continuous parameters. How many generators do I have? 3. Over here, to specify rotation, we had to specify 1 angle. And there was 1 generator. That's also a general rule. If you have a group element and you need to specify n parameters for the transformation, you will have a total of n generators. So what that tells you is we have gone from considering the properties of an infinite number of group elements to considering the properties of a finite number of generators. That's what we've gained by doing this. Okay. Now, we did some work yesterday, and yesterday we learned that we should focus our attention on the irreducible inequivalent representations. Now we've said that we're going to focus our attention on the generators. A natural question to ask is, if we want to focus on the inequivalent irreducible representations, what does that imply for the generators? What should we be focusing on at the level of the generators? And to figure that out, we're going to explore a few properties of the matrix exponential. So let's write down our group element. E to the I alpha, I'll call my generator T, and I'm going to perform a similarity transform on this group element. So here is an A to the minus 1. Here is an A. And what I would like to do now is I'd like to ask, what is the effect of the similarity transform on the group element? And to see this, we can do it as follows. So what should we think of for the exponential? Well, that's easy. We should power expand it. It's defined by its power expansion. Plus I alpha t minus alpha squared over 2 factorial t squared dot, dot, dot. And an A to the minus 1. Now I'm going to start multiplying this A and the A to the minus 1 in. For the first term, A times A to the minus 1 is just 1, plus I alpha. Now I get AT A to the minus 1 for that second term. Then we come to the next term. This is minus alpha squared over 2 factorial. I have an A. I'm going to write this as a T A to the minus 1 A T A to the minus 1. And you'll notice that what sits here is just a fancy way of writing T squared, right? Because the A to the minus 1 times the A is the identity. T times T is T squared. And so it continues. But if I look at this, well, what is this? This is 1 plus I alpha, AT A to the minus 1, minus alpha squared over 2 factorial, AT A to the minus 1 squared, and so it continues. Well, this is just the power series expansion of e to the I alpha A T A to the minus 1. So if you want to perform a similarity transformation on your group element, that's equivalent to performing a similarity transformation on your generator. So when we said that we only wanted to consider representations that were inequivalent, we could now say to ourselves, we only want to consider sets of generators which are inequivalent. So the statement that we found yesterday for the representation carries straight over for the generator. Are there any questions on that? Everybody happy with the conclusion? Does that mean yes? Good. Okay. So now let's ask ourselves, what about reducible? Well, if a matrix has a block diagonal structure, so let's say that we're considering some matrix T, and T has a block diagonal structure. There's a naught, there's a naught, there's a T2. I'm going to consider 3 blocks. Of course, it could be any number of blocks. Then one of the things I'll leave you to check, maybe you can see it immediately, is that if I were to raise T to the power of n, this block diagonal structure is preserved. And all that I get is each of the blocks inside my matrix are now raised to the power of n. So if I was looking for a group element that was reducible, so I want my group element to be block diagonal, well, I know that e to the I alpha t is equal to some sum from n is equal to 0 to infinity, I alpha to the n over n factorial t to the n. If I want this to be block diagonal, that will certainly be the case if all of these are block diagonal, the t raised to the power of n. And those will be block diagonal if t itself is block diagonal. So if I want the group element to be reducible, I can ask if the generator is reducible. Equivalently, if I want to focus on irreducible representations for the group, I will focus on irreducible generators. So we see that our statements about equivalence and reducibility that were made at the level of the generators, that were made at the level of the representation, the group elements, they actually carry right over for the generators. Okay, good. So it does seem like we're going to get out of our difficulty if we focus attention on the generators of the group. But when we wrote down our multiplication table, this was what we said was the specification of the group. So the one thing I could ask myself now was, well, what replaces the multiplication table at the level of the generators? I haven't told you that yet, right? And the thing that will replace the multiplication table at the level of the generators will also be a complete specification of the group. To figure out what that is, well, I guess we should start off with the multiplication table. Now, we can't write the multiplication table down, but we can do the following. We've got a continuous group, so we're going to make a couple of assumptions now. So let's imagine that we wanted to compose this group element, and I've parameterized it by some coordinates x prime. Let's imagine that we wanted to compose that with t, and I parameterized this by some coordinates x. So the x's and the x primes, they may be angles of a rotation, they may be displacements of a translation, they could be rapidities of a boost. They're just labels for the transformation. Once I compose these two, I will get another generator of the group, and the first coordinate here will be a function of the coordinates that appear inside those two generators, going all the way up to the nth coordinate. Okay, so that's now how I write down my composition law. Are there any questions on that? Anyone who's a bit confused, not quite sure what I'm doing?
Why some of the arguments to the function primed?
Okay, well, over here, so if I've got this t, what do I have to do to get a transformation? I have to specify what I'm going to stick into these n slots, what coordinates I should evaluate this at to get a specific generator, okay? Now, I have composed this group element with this group element. If I've composed those two group elements, okay, I will get another group element on this side. The group element that I will get will depend on both of the group elements that I've composed on this side of the equation. So what I will have to plug into the first argument of t will depend on both the x prime and the x. So this would be a function now of two n coordinates, n x's and n x primes. This only depends on n x primes, that only on n x's. Okay, does that help? Any other questions? Okay. So now we will make a couple of assumptions. Yes. Sorry, who's there. You mean over here? This is a prime. Yes. Okay, you happy with that? Good. Okay. So we're going to make an assumption now. And what we will assume is we will assume that these functions fi, so we've got fi of x1, x2, so on, xn minus 1 prime, xn prime. We will assume that they are smooth functions of the xi and the xi prime. Okay? When you're making this assumption, you're actually focusing on a Lie group. Okay? And that's what we're doing here. We're focusing on a Lie group. So we will assume that these are smooth functions of the xi and the xi prime. And we're going to make one more assumption. We are going to assume that the group element that you would get, if you set all of these coordinates to 0, would be the identity. Okay? And I guess that makes a lot of sense, because you can see, according to this rule over here, if we were to set alpha to 0, we've got e to the 0, which is a 1. Over here, if we set ax, ay, and az equal to 0, we again get e to the 0, which is 1. So that's pretty natural, and it's consistent with the type of way we were writing down generators, group elements in terms of generators before. Okay, good. So let's see if we can say anything about these f's. Well, I guess there is something we can say immediately. Let's say that we took this expression over here, and we evaluate it with all of the x primes equal to 0. If all of the x primes are equal to 0, then what is this statement saying? The identity multiplied by t. But we know what that is. That's got to be t. So what we could say is, if we have fi, we're now going to put all of the primes to 0. So we have got x1, x2, going all the way up to xn. And now I'm starting with the prime coordinates, and I put all of the prime coordinates equal to 0. So how many zeros are there here? N, and I've put all of the prime coordinates to 0. So let me make that n better. There's a better n. This would be equal to xi. Okay? But we could also have chosen to set all of the x's to 0. If we set all of the x's to 0, then we would have learned that fi of 0, 0, going all the way up to here, 0, x1 prime, x2 prime, xn prime would have to be equal to xi prime. Okay, everybody happy with that? So I haven't said too much. I've just said what the multiplication rule must turn into if one of those elements that I'm multiplying is the identity. But now, this allows me to write down an expansion for f, at least when these coordinates x are small. And it looks like this. So if I think about it, so I want to write down fi. Do you think I could have a constant appearing? Think so? Let's put a constant in. So let's put a constant in, and we'll see if we actually allowed that or not. So we'll have a ci over there. Let's maybe have a di times by, let's say a dij times by xj, and maybe an eij times by xj prime plus, and we'll take care of the x squared terms in a moment. Let's put all of the x's equal to naught. If we were to put the x's equal to naught, that term would disappear, right? We'd be left with the constant plus the x prime, but we know that we should just be getting xi prime. Okay? So from this equation over here, so let's call this 1 and 2, it tells us that this will have to be equal to delta ij, the Kronecker delta, and it tells us that this constant over here must be equal to 0. Is everyone happy with that or not? Okay, so what am I doing? I'm just saying, let's put the x is equal to naught. If I put the x is equal to naught, that term disappears, so I'm left with these two terms. But I also know that f has to be equal to xi prime. So I have to kill the constant. That can't possibly be there. And this has to be a delta function, Kronecker delta. But I could also put the x primes to 0, and then I know I must get an xi. If I put the x primes to 0, well, here's a second argument to say that the c must be 0. And now dij would have to be equal to delta ij. Everyone happy with that? Okay, so I'm going to fix up my expansion now. So I shouldn't have the ci. That shouldn't be there. I should just have an xi. And I should have an xi prime. Good. So at this stage, I've written down f to linear order. It has to look like that to be consistent with these two conditions. Now, what about at second order? We'll need the second order terms. Well, I guess I could have a term that looks like ci, j, k, xj, xk prime. I guess I could also have a term like dijk, xj, xk. And perhaps I could also have a term that looks like eijk, xj prime, xk prime. Now let's see, is this consistent with our two equations above? So let's look at equation number 1. Well, in this equation we set x prime to 0. If we set x prime to 0, that term goes away, so that's gone. So forget about that. That term is gone. That term is gone. So I'm left with x plus that. But in fact, I must only get x. So what that tells me is that term has to be equal to 0. In exactly the same way, if I was to set x prime to 0, or x to 0, I could learn that that term also should not be there. So to second order in x and x prime, this is the expansion of f. There would, of course, be corrections to this. How large would those corrections be? They would be stuff like, well, it would be x squared, x primes, and maybe an x prime squared x, stuff like that, that would start to contribute next. So I've dropped those terms. I'm assuming that x and x prime are small. Okay. And then the next thing that I want to do, I'm also going to assume that my group element can be expanded around the identity. So now I'm going to start working in a specific representation. Let's say representation gamma. And I'm going to expand this about the identity as follows. I must have 1 plus I xa ta. Okay? Now this would just be an infinitesimal transformation over here. So what is this TA? TA is my generator, right? So this would be the generator. So now the generator starts to make an appearance. And over here, I should say that all repeated indices are summed. So I'm summing over the J and K. I'm summing over A here. Okay? And I can add in a term at order x squared, which might look like 1/2 xa xb tab. Now, you can see that I am contracting this t over here with xa xb, and xa xb is symmetric under swapping the two x's. So what that means is this is symmetric in a and b. if I perform this contraction, only the symmetric piece of TAB will survive. So if I was doing the calculation and at some later stage I find something depends crucially on the anti-symmetric piece of T, I've made a mistake, because T's got to be symmetric. So I want to make a note of that. T is symmetric. Okay. Now that we've got that information, we can start to figure out what the generators will have to obey. So I'm going to take my group multiplication law at the top of this board, and I'm just going to write it down and multiply it out. So at the top there, I've got coordinates x prime. So when I plug it into here, what I'll end up getting is 1 plus I xa prime ta plus 1/2 xa prime xb prime tab plus whatever. And this will now have to multiply into the generator, the group element, with coordinates x. So I'm going to use my expansion again, but now with coordinates x. So this multiplies into 1 plus I xa ta plus 1/2 xa xb tab. And let's just see, what is this equal to? Well, the 1 times the 1, that's easy. So that's a 1. Plus we'll have an I xa ta plus I xa prime ta. We will have a 1/2 xa xb tab. We will have a 1/2 xa prime xb prime tab, and we would have a term coming from multiplying that with that, which would give us a minus xa xb prime ta tb. Okay? And then plus, we would have the x cubed type term starting to appear. I'm only working to second order. What must this be equal to? So I've multiplied the two group elements. Well, I've said that that must be t evaluated at the f's, right? So now let me plug the f's in again to this expansion. So this should be equal to 1 plus I fa ta plus 1/2 fa fb tab. But I know what f is. Okay, we argued f has to take that form. So let me now plug in the expression for f. So this will be 1 plus I need an xa plus x a prime plus c, let's say a, b, c, xb, xc prime, and that contracts into ta, plus, and now I'm only working to second order, so I only need to include the first order contributions to fa and fb. So this is 1/2 xa plus xa prime xb plus xb prime tab. Okay. So I've got a 1 plus I xa ta plus I xa prime ta. Good. Those first three terms match those first three terms. Now I'm going to start picking up terms from here. I'm going to pick up the xa xb tab. Good. That matches the next term. I'm going to pick up the term with the x primes. That also matches. And now let's look at the term with the xx prime. Well, there's a couple of contributions. Here's one. We've got c, a, b, c, xb, xc prime, ta, plus Now we've got some terms coming from multiplying that with that and that with that. Now, I already said TAB is symmetric, so I'm just going to multiply them in and add them. And you can check that what I will get is an XA, XB prime, TAB. The factor of 1/2 over here gets cancelled because I've added two terms. Okay, good. In this term? Great. Okay, good. Ah, good. Okay. So I guess there should also be... Oh, right. Yeah, good point. Okay. Is that the only thing I missed so far? Okay, good. Okay. Plus order x cubed again. So you see everything matches. That matches, that matches, that matches, that matches, that matches. But this has to now be equal to that. Okay? That's the condition. So let's write down. So I'm going to read that off now. You should be able to check that. I mean, I just did the same calculation in my notebook, so it should be the same thing. What we learn is the following. Minus TATB would be equal to TBA plus I TCEAB. But we said that TBA has to be symmetric. Okay? So what we have to require is, we have to require for consistency that naught is equal to TAB minus TBA. Okay? And what does this mean? Well, if you work out what this means, it means the following. So okay. TBA would be equal to what? It's minus TA TB minus ITE CEAB. So you use this formula. You ask that that is 0. And this is the condition that you get. This implies that TA TB is equal to I F A B C TC, and this FABE is equal to CEAB minus CEBA. So let's just pause to see what we've done. We said, okay, let's start to focus on things at the level of group generators. There's only a finite number of those, and we'll get a better characterization of the group. Now, previously we've been characterizing our group by its multiplication table. We wanted to figure out what do we replace the multiplication table by when we are focusing on generators. And we now have our answer. We have to require that the generators satisfy this relation. We call that the Lie algebra of the group. Okay, so this is called the Lie algebra. And these constants, F, A, B, C, these are called the structure constants of the group. And modulo some subtleties that we will discuss, the structure constants form a fingerprint of the group, just like the multiplication table did. So you want to specify your Lie group, specify the structure constants. Another comment maybe, why do we have this I sitting here in the algebra? Well, there is a reason for that. So we've said that our generators, the TAs, are Hermitian. Okay? So let's take a look at TATB. So if we look at this commutator, TATB, this is equal to TATB minus TB, TA. And let's take the dagger of that. When we dagger a string of operators, we need to reverse the order of the operators, and we need to dagger each operator. Okay? Now these guys dagger to themselves because they're Hermitian, which means we land up just swapping the order of them. So the first term becomes TBTA, and the second term becomes TATB. So this is just minus TATB. Okay, everyone happy with that? So this is anti-Hermitian. But I times by something that is Hermitian is anti-Hermitian. So that means if I include this I here, my structure constants will be real. That's why I included the I. Okay? So the I is in the Lie algebra, so the structure constants are real. Let me just check. Another important comment. So something may be worrying you. You might say, you know what, I don't find this convincing at all. And the reason why I don't find it convincing is you've worked things out to order x squared. And you dropped the x cubed and all of that. Now, just to make the x squared terms agree, we had to impose this condition. What about if I went to x cubed? I mean, would those terms just agree automatically, or would I get new conditions? Okay? So my challenge to you is check those terms. You should find that there are no new conditions that need to be satisfied. Once you've got the Lie algebra condition holding, you know that your group multiplication will be consistent. Okay. And now let's come back to one of the subtle points that I mentioned. We've been making an assumption. The assumption that we've been making is if we exponentiate the generator, we'll be able to get any element of the group. Now, in certain situations, there are elements of the group that you cannot obtain by exponentiating the generator. So I want to give you an example of that, an example of generators of a group that could not be obtained, of group elements that could not be obtained by exponentiating a generator. Okay. And the example that I want to consider, so it's called SO2, or O2, sorry. So we're going to look at the group O2. So what is the group O2? It's a matrix, well, it's isomorphic to the matrix, let's say, the group of 2 by 2 real orthogonal matrices. And what we mean by orthogonal matrices, we mean that if you calculate A transpose A, that is the same as A transpose, that just gives you the identity. Okay. So the first thing, if I tell you something like this, the first thing that you should check is the condition that we're imposing on our set of matrices, is that consistent with the closure axiom of the group? So what I mean by that is, let's say that I've got A1 transpose A1 is equal to the identity. And let's say that I've also got A2 transpose A2 is equal to the identity. That means that A1 and A2 will both belong to the set of matrices. The question now is, if we really have closure, does A1 times A2 belong to the set of matrices? Well, let's check that. So we take A1, A2 transpose times by A1, A2. Now, if I take the transpose of a string of matrices, what should I do? Reverse the order of the matrices and transpose each matrix. So this would now give me A2 transpose, A1 transpose, A1, A2. A1 transpose A1 would just be the identity. So I'd land up with A2 transpose A2, and that would also be the identity. Good. So if I start off with two matrices which satisfy my condition of orthogonality, and I multiply them, I get a matrix which also satisfies my condition for orthogonality. So that's the most basic thing you could check. Now, we know the following. We know that the determinant of a matrix A is equal to the determinant of the transpose of the matrix. So, and we also know if we have got a product of matrices, the determinant is equal to the product of the determinants. So let's take a look at this condition over here. What is the determinant of the unit matrix? 1, right? So what we learn is, we learn that the det of A squared is equal to 1. So I've taken the determinant of this equation. And that tells me the determinant of A can be plus or minus 1. In O2, I have some elements which have a determinant equal to plus 1 and some elements with a determinant equal to minus 1. Those elements with a determinant equal to plus 1 are just our normal rotations. But you see, there's another type of matrix that satisfies this condition. And that's not just a rotation. It's a rotation together with, you leave one of your axes the same and you flip the other one. So you've got some sort of parity transformation that you've performed. What distinguishes them? Well, we can rotate a rigid body. We cannot do that parity flip for a rigid body. So those subset of matrices with determinant equal to plus 1, we call them proper rotations. Those are rotations we could perform on a rigid body. The subset of matrices with determinant equal to minus 1, we would call them improper rotations. We cannot perform them on a rigid body. Now, if I take my matrix and I vary it continuously, oh, great. I feel much better. Okay. So if we take a look at this, how do I know that it's the matrices with theta equal to plus 1 that can be reached? Well, I know that if I was to set all of my parameters equal to naught, I would get the identity, right? So I'm considering smooth deformations away from the identity. And the identity as a determinant of A is equal to plus 1. So that's how I would know which of those two sets I have got. So let me tell you how you would get those elements with theta equal to minus 1. And you can try to convince yourself that this is true in general. So if you take a look at this matrix, so you've seen that matrix already. And we take that matrix, so let's call this A. You can check that A transpose A is equal to 1. And you can also check that the det of A is equal to minus 1. Now, my claim to you, so this is a nice thing to try to prove. You can look for a counterexample first, I guess, is to show that any A with det A equal to minus 1 can be written as 0, 1, 1, 0 times by a proper rotation. So multiplied by one of the rotations with theta equal to plus 1. You'll often see a picture drawn in textbooks which looks something like this. So there's two sheets, and this is now meant to be a picture of O2. The identity lives in one of these sheets, and by moving smoothly away from the identity, we can explore all of the elements sitting on this sheet. So this sheet itself forms a subgroup called SO2. If you look at the set of matrices with determinant A is equal to plus 1, that forms a subset. And if you check, does that subset satisfy the axiom of a group? Yes, it does. Another way of talking about this, we say that O2 is disconnected, and it has two disconnected components. So if you see any of this terminology, this is what people mean. Okay, so where did we start off? Well, our starting point was we said to ourselves, what would be good labels for a particle? And what we meant by that is, what observables would be invariant under a set of transformations I could consider. But I could consider almost the exact opposite of that question. So I could do the following. I could say, well, let me tell you what the good labels are. And why don't you tell me what the group of transformations are that will leave those labels invariant? That's a useful way to think in group theory. So it may be that in nature we've noticed something that stays constant, and we would now like to figure out what group of transformations would leave that particular thing constant. Okay. So let's start off with these examples over here. Let's consider a real vector with d components. So we will have some vector u with components I, and maybe some vector v with components I, and we will have a sum from I is equal to 1 to d. These are real vectors. And I may ask myself, well, what group of transformations leaves this set of this particular quantity unchanged? I'm going to write this in Dirac notation, okay? Just remember, because we're dealing with real vectors, to get the bra from the ket, you just transpose. You don't take a complex conjugate. Everything is real. Okay. And our transformation that we will consider, set of transformations, will take vi into, so we'll have some sum. So I'm writing sums explicitly, but repeated indices are summed. Aij, vj. How would this transform? Well, if we look at uv, what would this turn into? So here, of course, this means that v goes into a times by v. And if I take the transpose of that equation to get the equation in terms of the bras, I would get v would go into v a transpose. Okay, so what would this go into? Well, this would go into u a transpose a v. And if this is really going to be invariant, well, this has to be equal to uv. I'm going to write uv in a slightly different way. I'm just going to write this as u times by the identity times by v. For which vectors u and v must this hold? This must hold for all vectors u and v. Because it holds for all vectors u and v, I know that this is not just a statement for a particular matrix element. It is a statement for all matrix elements. So I can take this equation and promote it to a matrix equation. And the matrix equation that I find out is A transpose is equal to 1. So here, in d dimensions, I've recovered the O2 example at the top there. So what is O2? O2 would be that group that would leave the inner product of two-dimensional vectors invariant. I could think of adding in one more invariant. And the next invariant that I could add would look like this. I take, in d dimensions, the completely antisymmetric tensor. So what properties does this guy have? If you swap two indices, any two indices, it picks up a minus sign. Okay? Once I've told you that, you know that if any two indices are the same on that tensor, this has to be equal to 0. And the only other piece of information I need to give you one value of the tensor. And then you can work out all others. Well, the value that I will give you is that epsilon 1, 2, 3, so on up to d is equal to plus 1. Now, another quantity that I could consider would be this. I'll take d vectors, and these indices are all summed. And now I say, I would also like this to be invariant. If I transform this, how does it transform? Well, this would turn into epsilon I1, I2, up to ID. I have got an IA1, J1, IA2, J2, ID, JD, contracted onto my vectors U, J1, V, J2, W, JD. So that's how it would transform. Each vector has picked up a factor of this matrix A. Now I want to study this object over here. What does this thing look like? Well, if I take I1, I2, up to ID, AI1, J1, AI2, J2, up to ID, JD. What I would like to do now is I'm going to relabel two indices. So what I call I1, I will now call I2. What I call I2, I will now call I1. So I can relabel dummy indices. This is epsilon I2, I1, up to ID. Then I would get A, I2, J1, A, I1, J2, going all the way up to A, ID, JD. This is equal to, I'm going to swap these two indices back. When I do that, it costs me a minus sign. Minus epsilon I1, I2, ID. And I can swap these two around. I mean, these are just numbers. They're not matrices. They're actual matrix elements. I1, J2, AI2, J1. Everything else unchanged. So how is this related to this? Well, I swapped J1 and J2, and I picked up a minus sign. So what this tells me is this thing is completely antisymmetric in the indices J1, J2, up to JD. So once again, I only have to give you one value of it. The value that I will give you is this one. Epsilon I1, I2, up to ID, A, I1, 1. A, I2, 2. All the way up to A, ID, D. And if you go away and write this out, maybe you want to only do it for a 2 by 2 matrix, you can easily check for yourself that this is in fact just the determinant of A. So what we have here, this quantity over here, so let me clean that. I've now figured out what this coefficient was. So what is this equal to? This is equal to the determinant of A, epsilon J1, J2, up to JD, U J1, V J2, up to W JD. So if I require that both that is an invariant and this object is an invariant, now I've got SOD. Only those matrices with a determinant equal to +1, because that's the only way this would be invariant. Okay? So you can see that now we've turned the whole story on its head, and we've said that we started off and we said that we wanted labels that were invariant, and now we've seen that by stating what labels we would like to be invariant, we actually get a specification for what group we would like to look at. Are there any questions at this point? Yep.
The epsilon has a lot of indices.
Yes.
Can you restrict them to about 3 indices for me to see what will happen?
Sure. You mean over here?
Epsilon 1, 2, 3, 2, let's say equals +1.
Yes.
That's too long for me.
Okay.
Can you shorten it? And then
Sure.
reduce it?
Would you like me to redo this argument with 3 indices?
Yeah, something like
Sure. Okay. So what we are saying is we want this to be true. Sum from I is equal to 1 to 3 of ui vi. That's one thing that I don't want to change under my transformation, okay? And if we just ask that this doesn't change, we've already figured out that that means that A transpose A must be equal to 1. But now I want to put in an extra condition. I also want epsilon I1, I2, I3, ui1, vi2, wi3. I also want that to be invariant for any 3 vectors u, v, and w. Okay? So let's see how this thing would change. Well, I know what I should do. So, for example, if I was looking at the w, the v, I know that vi2 would turn into ai2, j2, v, j2. And these indices are summed, okay? It would just pick up a factor of a up front. That's our transformation rule. So I'm going to pick up one factor of a for each vector. So this is equal to epsilon I1, I2, I3, a I1, J1, a I2, J2, a I3, J3. And now let's put the 3 vectors in. U, J1, V, J2, W, J3. Yep.
Can you just write the indices a little bigger? We can't see the...
Sorry, I can do that. Factor of 2?
Yeah, factor of 2.
Okay. So what would I like this to be equal to? That's okay? Let's say J1, J2, J3, U, J1, V, J2, W, J3. Okay? If that's going to be true, what I want is I want this coefficient to be equal to that there. So the condition that I'm actually asking for is epsilon J1, J2, J3 has to be equal to epsilon I1, I2, I3, A, I1, J1, A, I2, J2, A, I3, J3. So that's what I would like to happen. The next step of the argument is I said, okay, so this side is certainly antisymmetric when I swap J1, J2, and J3. So I better check that this side is antisymmetric when I swap J1 and J2 or J2 and J3 or something like that, okay? So let's check that. That's the first part of the argument. So if I take epsilon I1, I2, I3, A, I1, J1, A, I2, J2, A, I3, J3, this is equal to. First thing that I'm going to do, I'm going to call I2, I1, and I'm going to call I1, I2. Okay? I can just relabel dummy indices. So this will now be epsilon I2, I1, I3, A, I2, J1, A, I1, J2, A, I3, J3. And now what I can do is I can swap these two indices. That'll cost me a minus sign. And I can swap these two factors around. They're just numbers. So you can see, if I swap J1 and J2, which is what I've done here, I pick up a minus sign. Okay, you happy with that? So now, all that I have to do is, if this is totally antisymmetric, it's only going to be non-zero when J1, J2, and J3 each take different values. So I'll give you the value when J1 is equal to 1, J2 is equal to 2, and J3 is equal to 3. Okay? In that case, we have epsilon I1, I2, I3, A, I1, 1, A, I2, 2, A, I3, 3. And this is another way of writing down the determinant of a 3 by 3 matrix. I mean, in fact, you know that taking a determinant in 3 dimensions is like taking cross products, right? Which you can do with epsilon. So if you like, these are the rows or columns of the matrix, and we're taking the cross product. Maybe if you think about it like that, you can see the result. So then what is this equal to? Well, this is actually equal to the determinant of A times by epsilon J1, J2, J3. So that means I must have the determinant of A equal to plus 1. So I'm now focusing on SOD, only those matrices with determinant equal to plus 1. Okay? So requiring these two invariants means I'm left with now just proper rotations. Yes, Noreen?
Just maybe you could remind us the two conditions that we want to, two identities we want to hold, and the one is a scalar product, the other one is singularly epsilon.
Yes.
Something reminds me of the volume of some kind. Can you tell us what physically...
The epsilon is?
both conditions that we want to be preserved.
Okay, so the two conditions that we want to be preserved is we preserve the scalar product between any two vectors. Okay, you happy with that? And the other one is this contraction of the epsilon with the u, v, and the w. If you want to know what is the physical interpretation of this thing, this would be the volume traced out by those three vectors. So that's what we're trying to also keep invariant by this transformation. Okay? If you were to perform a parity, that guy would change sign. Okay, you'd be reversing the orientation of those three vectors. Yep.
Sorry, Robert. Perhaps this is a good opportunity just to point out that in your naming of the group SO2,
Yes.
or SO3, how the S relates or what conditions.
Okay, so that's a good point. So what we've got here is, so let's think about how we're naming these groups. If we have OD, okay, the O stands for orthogonal. So when we have orthogonal, we mean A transpose A is equal to 1. That's what the O is telling you. The D tells you these are D by D matrices. If you look at SOD, we have the O, so we're still looking at orthogonal matrices. We have the D, they're still D by D, but the S stands for special. You're looking at that subset which has determinant equal to +1. If you're looking at UN, for example, and you went to SUN, so you've added the S again, you're again saying that you're looking at those set of matrices with determinant equal to +1. Okay? Any other questions at this point? So these have all been good questions. Okay. So now, so maybe I've got time to do one last thing, which is the following. Let's ask ourselves for SOD, what would the generators look like? Well, we would like A transpose A to be equal to +1. So if we think that we're going to write A is equal to E to the I alpha T, where T is our generator, then we want A transpose, which is E to the I alpha T transpose, to be equal to A to the -1, which is E to the minus I alpha T. Okay, so to get the inverse, I just put a minus up front there. If I now compare that to that, I learn that T transpose must be equal to -T. Now, these matrices we said were Hermitian. If they are Hermitian and they are antisymmetric, what do they have to look like? Pure imaginary, right? Antisymmetric and Hermitian. That's exactly the form that we found over here when we started off by considering a rotation. This was an element of SO2. So what are our generators going to look like in general? In general, we will have a D by D matrix, and we will have, so we could have elements like this. So let's say that this is column I, that's column J. This is row I, this is row J. If I put an I sitting over here, I would put a minus I sitting over here, and zeros everywhere else. And then I could take linear combinations of these with any coefficient sitting up there in the exponential to get an element of OD. How many of these generators are there? Well, these have to lie off the diagonal. So if I choose a value for I, and there's D ways to choose the value for I must now choose a value for J, which is not equal to I. So there's a total of D minus 1 choices left that I have for my second index. But if I just take this number, I've counted all of those elements above the diagonal as distinct from those below the diagonal. But I have to correlate them with the minus I and the I. They're certainly not independent. So I need to divide by 2. So that's the number of generators that we have. Now, if you remember, we said the number of generators would match to the number of parameters that we have to label our transformation. Can anybody tell me how many rotations we have in D dimensions? When we have a rotation, what do? We rotate in a plane. It's only in 3 dimensions that we can get fooled into thinking we rotate about an axis. We usually rotate in a plane. So we rotate in the XY plane or the YZ plane. How many planes are there in D dimensions? So if I was you and I didn't know, I would guess D times D minus 1 over 2. right? This is how many planes there are, and let's try to figure out why. To specify a plane, you have to specify 2 coordinates. So choose your first coordinate. I'm doing the same counting, any one of D. Choose your second coordinate, any one of D minus 1. But the xy plane is the same thing as the yx plane, so I better divide by 2. So this number has come out equal to the number of planes that we have in D dimensions, as it would have to, because that's the number of rotations we would have in D dimensions. Sorry? Sorry, Bob. Oh, could I repeat it? Sure. So the fact that our number of generators has come out equal to D times D minus 1 over 2, if you remember, that means that we've got D times D minus 1 over 2 parameters labeling our transformation. And a natural way to understand that is that in D dimensions, we have a total of D times D minus 1 over 2 planes. So it's natural to expect we've got a total of D times D minus 1 over 2 independent rotations that we could perform. So that's where that number's coming from. Okay?
What I wanted to explain is why you have D minus 1 over 2 number of planes that you have in dimensions.
Okay. Let's imagine we're working in 2 dimensions, x and y. How many planes do we have in 2 dimensions? 1, right? So let's plug in a 2 there. 2 times 2 minus 1, that's 2 times 1 over 2, that's a 1. Now let's think in 3 dimensions. So how many planes do I have in 3 dimensions? I've either got xy, xz, or yz, total of 3 planes, right? Sure. So let me make sure. Oh boy, you want right-handed, so let's just check. Okay, so I'll do this. That's okay. Now, how many planes do we have? We've got 1 plane sitting over here, the xy plane. We've got a plane sitting over here, zy, and we've got a plane over here, zx. Are you happy with that? In general, if I wanted to specify a plane, what would I have to do? I have to specify 2 coordinate axes. When I want to choose the first coordinate axis in t dimensions, how many choices do I have? D. You happy with that? So I would have a D. Then I have to choose a second coordinate axis. Now, I don't have an xx plane, right? I have to choose another coordinate axis. So after I've chosen my first one, I've got D minus 1 possible choices left. So I'd have that times by D minus 1. But if I count like this, I'm going to get it wrong, because I'm going to say x times y, which was one of the choices I counted, and then another choice that I counted was yx. And those are not independent. Those are the same plane. I've only got the xy plane. And that's why I divide by 2. Does that help? Okay. Any other questions? Okay, I guess this is a good place to stop.